Okay, so yesterday I talked about, maybe let me go back here. So I talked about stacks and two perspectives on stacks in terms of atlases, so in terms of Lie groupoids, or in terms of a more abstract point of view in terms of sheaves of groupoids. Okay, and I ended with the definition of differential forms on stacks. So again, you can think of them either in terms of the abstract definition, or if you have a representation in terms of the groupoid, there's a nice double complex computing such differential forms. So it's some kind of groupoid cohomology of the de Rham algebra. Okay, and yeah, maybe let me again repeat this example that if you have a closed P-form degree 1 on M mod G on the quotient stack, it's not strictly closed. So there's a P-form on the arrows, and there's a P+1 form on the objects of the groupoid. And the closure of the P-form on the arrows is controlled by that P+1 form on the objects. Okay, and then so you can define the notion of a shifted symplectic structure. So it's going to be a closed to form of degree n. So again, this notion that I just talked about. Again, whenever I say closed, I mean homotopically closed. Such that the induced map from the tangent complex to the cotangent complex shifted appropriately because you have a form of degree n is a quasi-isomorphism in this DG category, so an equivalence in this DG category. Maybe let me recall again that this DG category of quasi-coherent complexes in the case of a quotient stack, this is the DG category of representations up to homotopy. Okay, so you have the tangent complex, the joint representation up to homotopy, and the cojoint representation up to homotopy, and you have a map of representations up to homotopy. Okay, so besides the notion of shifted symplectic structures, there is also a notion of a shifted Lagrangian structure. So whenever you have a morphism, you can talk about what it means. So if the target is symplectic, you can talk about what it means to be Lagrangian. There's no requirement for this to be an embedding or anything like that, but in the classical setting, it will be forced to be an embedding. So not necessarily an embedding. And also, let me emphasize that this is a structure rather than a property of a submanifold being Lagrangian. And finally, a somewhat new feature, which people have observed before as well, is that if you have two Lagrangians in a symplectic manifold, then their intersection has a shifted symplectic structure of shift one less. So maybe I'll refer you to Kai Berenstock, who will talk more about this. That's my name. Okay, so that's the setup for shifted symplectic structures. Again, let me emphasize that maybe the last bullet point is the most unfamiliar. Okay, so now I want to go through some examples of shifted symplectic structures, and I want to begin with the example of one shifted symplectic structures. And again, to give some examples, I want to explain what are one-shifted symplectic structures on quotients by some groupoids. So let's say you have G over M, a groupoid. And then, well, by definition, one-shifted symplectic structure is going to be a closed two form of degree 1. So it's going to be a multiplicative 2 form on the arrows and a closed 3 form on the objects, with this compatibility condition. so the closure of omega is controlled by the check differential of applied to that 3 form. Okay, so that's what a closed 2 form is. And then you want to say non-degeneracy. Well, again, non-degeneracy says that the map from the adjoint representation to the coadjoint representation of the groupoid is a quasi-isomorphism. They have these 2-term complexes in degrees -1 and 0. And you have a map between them. And you want this map to be a quasi-isomorphism. You can rephrase this in an easier way. So out of this map of 2-term complexes, you can construct an exact sequence, L to T plus T star to L dual. And the first map being a quasi-isomorphism is the same as saying that this is an exact sequence. Okay, so you see that this condition of the top map being a quasi-isomorphism is the same as saying that L is a Dirac structure. It's an exact Dirac structure. Okay, and then so this kind of non-degeneracy condition on symplectic shifted symplectic structures is exactly what Xu define as quasi-symplectic groupoids. Okay, so the upshot is that one-shifted symplectic structures on quotient stacks by groupoids are the same as quasi-symplectic structures on a groupoid. Okay, and then you can also get the usual symplectic groupoids. So symplectic groupoids correspond to the case when H is 0 and the non-degeneracy condition is strict. So that the multiplicity of 2 form on the arrows is strictly non-degenerate. And these correspond to pairs of a shifted symplectic structure on a quotient and a Lagrangian structure on a projection. Okay, so this is not a meridian invariant notion because I have some structure on a projection, the Lagrangian structure, while quasi-symplectic groupoids just correspond to one shifted symplectic structure on a quotient. This is independent of the choice of the cover, so this is manifestly meridian invariant. Okay, and it's been known for a long time that quasi-symplectic groupoids or one-shifted symplectic structures are closely related to moment maps for symplectic manifolds. And for instance, there is this relationship between Hamiltonian LG spaces, so Hamiltonian spaces for the Lie group, and quasi-Hamiltonian G spaces. So this was explained in the paper about Malkin and Myronkin. And there's an interpretation of this correspondence in terms of either one-shifted symplectic structures or quasi-symplectic groupoids or something like that. Basically, if you look at the space of connections, so space of G bundles on the circle together with a connection, this has a natural one-shifted symplectic structure. And then you can look at the holonomy map to conjugacy classes, so G mod G. Both of these spaces are naturally one-shifted symplectic, and you can show that this holonomy map preserves one-shifted symplectic structures. So there was a related fact proved by Cabrera, Gualtieri, and Myronkin in terms of Dirac structures. So as I said, quasi-symplectic groupoids have infinitesimal information given by Dirac structures, so you can instead say something about Dirac structures. Okay, and Lagrangians in the object on the left correspond to Hamiltonian LG spaces, and Lagrangians in the object on the right correspond to quasi-Hamiltonian G spaces. Yeah.
Pavel, can I interrupt you for a second? Because there was a conversation yesterday among participants, I think about exactly your second bullet point. Because if you are given a quasi-symplectic groupoid, you can always choose a Moriti equivalence to a symplectic groupoid.
Mm-hmm.
So the way, and that's one aspect. The other aspect is if I have symplectic groupoids, there is a notion of symplectic motif equivalence.
Yeah.
And so there are these two different points of views that you can think of groupoids up to motif equivalence, or you can think about symplectic groupoids up to symplectic motif equivalence.
Yeah.
So how do you see this in your correspondence?
Well, so you can talk about some more, just plain motif equivalence just means you have an equivalence of stacks, just plain equivalence of stacks. So one thing is that you can transfer quasi-symplectic structures along motif equivalences, and that corresponds to the fact that if you have an equivalence of stacks and you have a closed non-degenerate differential form on one of them, you can transfer it. Or you can also, if you have quasi-symplectic structure on both, you can talk about symplectic, in the classical setting, diffeomorphisms, in this case, symplectic equivalences of symplectic stacks. So this is what it means for two quasi-symplectic or two one-shot symplectic structures to be equivalent. So this is the notion of a symplectic motif equivalence. Does it make sense?
I think it does, but there is an alternative approach where you change the site. You don't change the site. You enrich the site with extra structure so that the motif equivalences now become the symplectic motif equivalences.
I see. Yeah, I don't think about that kind of perspective. Let's say I prefer to think about stacks, maybe equipping them with extra structure rather than trying to look at the category of symplectic groupoids up to symplectic motif equivalence. Okay. Yeah. Any other questions? All right. So this was the case of one-shifted symplectic structures. Now I want to also mention two-shifted symplectic structures where they appear. So there's a notion of a symplectic double groupoid. So again, double groupoid is something, is a diagram like this, where all the double arrows are groupoids. And the symplectic double groupoid is something where D is equipped with a multiplicative symplectic structure such that both D to G1 and D to G2 are symplectic groupoids. So as far as I know, Weinstein introduced that to talk about integrations of Poisson groupoids. Okay, and then you can rephrase. So maybe let me go back to interpretation of double groupoids. So here I said that a double groupoid can be encoded in some diagram of stacks. So you can take quotient stacks of M with respect to G1, with respect to G2, and with respect to the double groupoid. And so you have this kind of commutative diagram with all the maps being covers. And you can also encode the data of a symplectic groupoid, symplectic double groupoid, in the same diagram, where now the bottom right, so the quotient by the double groupoid is two-shifted symplectic. Then these are Lagrangians. And then this map from M to the pullback, X cross Y over Z, is one-shifted Lagrangian. Okay. Okay, so that's relatively straightforward to see how this corresponds between symplectic double groupoids and sort of diagrams of symplectic and Lagrangian maps like this. Okay, and so in this diagram, I talked about the intersection, so X cross Y over Z. And you can ask, what's the meaning of that intersection? So I mentioned that yesterday, that this intersection is the same as the quotient of M by what's called the core groupoid. And for so if you start with a symplectic double groupoid, then the core groupoid will be an ordinary symplectic groupoid. And you can see it here. So there's a pullback diagram like this. And the condition was that this map from M to M mod C was Lagrangian. And as I said, if you have a atlas, which is a Lagrangian map that corresponds to the data of a symplectic groupoid.
Well, may I ask a question? Since those G1 and G2, they are Poisson groupoids normally, no? So isn't then M mod G1, say, directly one-shifted symplectic?
Yeah, so you could, so you could extract, let's see. So you said G1 over M is a Poisson groupoid. So that means that M mod G1 and M mod G2 are one-shifted Poisson. And same here. So I'll mention the relationship between Poisson structures and Lagrangians and so on later. But yes, so G1 over M and G2 over M are Poisson groupoids. So the quotients are not one-shifted symplectic, they're going to be one-shifted Poisson. Yeah. All right. Yeah, and as an example, you can look at this cotangent double groupoid. And this cotangent double groupoid, if you look at the quotient by that, so this kind of the deepest quotient, M mod G for the cotangent double groupoid, you'll see that this double groupoid presents a two-shifted cotangent bundle of the quotient. Okay, and that's a standard example of symplectic groupoid. And as you see, this one, it's a two-shifted cotangent bundle, so it's two-shifted symplectic. Okay. So the last thing I want to mention is, so I mentioned one-shifted symplectic structures and two-shifted symplectic structures. I also want to briefly mention three-shifted symplectic structures because they have appeared before. Okay, so far I've been talking about quotients by groupoids, and these are nice, well, algebraic stacks in the algebraic perspective or differentiable stacks in the differentiable perspective. But you can also consider stacks which are formal stacks, so quotients by Lie algebroids rather than quotients by groupoids. So basically, I want to say some theorems where I don't want to talk about integrations of current algebroids, what they mean, but that's essentially what's happening here. Okay, so if you like, you can think of this formal quotient as a quotient by some local groupoid integrating a given Lie algebroid. Okay, so the first fact is that the data of a twisted Courant algebroid is the same as a two-shifted symplectic structure and a quotient. And when I say twisted Courant algebroid, it's the same as the notion of a Courant algebroid where there's a twist by a 4 form. It's usually denoted by K. So there's a closed 4 form on M, and you can twist the data of a Courant algebroid by that. And so you can show that twisted Courant algebroids are the same as specifying a two-shifted symplectic structure and a quotient. And then a Dirac structure is the same as, so if you have some Lagrangian in E in the Courant algebroid, then it's going to be the same as a two-shifted Lagrangian map. So I just want to explain various levels of shifts and how they appear more classically. Yeah, and then there's this notion of a CA groupoid. So Courant algebroid in the category of groupoids, where E over G is a multiplicative Courant algebroid. So Courant algebroids explained correspond to two shifted symplectic structures, but then these are two shifted symplectic structures which are multiplicative. So on the quotient, they give rise to three shifted symplectic structures. Okay, so this is as far as I could see in literature how far people have gone. Of course, you can talk about higher analogs of Courant algebroids, and then you can get higher shifted symplectic structures in this way. Okay, so let me pause here because this is all I want to say about shifted symplectic structures. Next, I want to talk about shifted Poisson structures. Are there any questions?
Could you clarify in this theorem whether the Courant algebroid is exact or not, and whether the Dirac structures are, let's say, usual Dirac structures, or what their support is?
Yeah. The Courant algebroid in the first statement is not exact. Exact Courant algebroids correspond to the case when the anchor map, so E prime is a certain Lie2 algebroid you can obtain from a twisted Courant algebroid. And the exactness corresponds to this anchor map being an isomorphism. So in general, this is not an exact Courant algebroid. So for an exact Courant algebroid, you'd usually say that there's a twist by a closed three form, so the Schwerer class. Here, it's a higher notion of a twist. It's a twist by a four form. So these are non-exact Courant algebroids. And in the second statement, these are Dirac structures without support, or they're supported everywhere. But we also have a statement for literally the same statement. You just replace, yeah. I'm
a bit lost. What is the prime? What is the E prime or?
Yeah, so I haven't explained this. There's a correspondence. If you have a twisted Courant algebroid, or let's say Courant algebroid, so this is an ordinary vector bundle, you can obtain Lie2 algebroid. So this is, I guess, due to Edinburgh. So I haven't stated the statement precisely. The idea is that if you have any Lie infinity algebroid, E prime, and you specify a two-shifted symplectic structure, then it forces E prime to be a Lie2 algebroid, and then you can recover a twisted Courant algebroid out of this Lie2 algebroid. That's the statement. Does it make sense?
Yeah, thank you. Sorry.
Yeah, and to answer, I guess, Marco's question or someone's about Dirac structures we support. So here I have Lie algebroid and Courant algebroid over the same manifold. But you can also look at the case what happens if you have a Lie algebroid over a submanifold, and you ask about these Lagrangian maps where n is some submanifold, and you get exactly Dirac structures with support. Any other questions?
Is the pairing non-degenerate, or is it non-degenerate only whatever after you pass to cohomology? Just the definition of your twisted Courant algebra. So how much?
Yes, that's the point. That's somehow the difficult part of the theorem, to show that you start with this notion of a two-shifted symplectic structure, which is rather flabby, and there's a quasi-isomorphism of tangent complexes. And then the point is that you can always strictify it in some sense. So the closed two form, so it's a two form of degree 2. And the point is that it only has a 2 form and a 4 form, and the 2 form is strictly non-degenerate. So it's a kind of certification result. So this is why you see the twisted Courant algebroids. There's a twist by a 4 form. That's the part of the two-shifted symplectic structure.
Right. So well, Pavel, I think when you twist by 4 form, it's not Courant. It's only a twisted Courant, right?
Yeah.
It's more, yeah. It's like certain identity is not hold, but only up to this twist by 4 form.
Yeah, that's right. So one of the ways of phrasing that is that I guess the Jacobi identity holds up to K, and then symmetry holds up to the pairing.
Right. So what I guess what you want to say that Courant gives rise to this E prime, which is a Lie algebra, but twist Courant also give you E prime, right?
Yeah, that's right. Yeah. Okay. Yeah, any other questions? Okay, let me move on to shifted Poisson structures. So again, here's some facts that yeah, you know. So there was a paper called Shifted Poisson Structures by Kalak Pantev by Kevitsosi. And what they introduced is the following. So if you have a stack, there is some complex of n-shifted polar vector fields for the stack, and this carries, as you can see, it should be a commutative algebra, and in fact, it carries a Poisson structure, so the higher analog of the Schouten bracket. Okay, so and once you introduce polar vectors with its Schouten bracket, you can talk about n-shifted Poisson structures. So an n-shifted Poisson structure is going to be a Maurer-Cartan element in this algebra of polar vectors, but where you only see bivectors, trivectors, and so on. So yesterday, Camille gave a talk about shifted Poisson structures in differential geometry, and it was also, the definition was some Maurer-Cartan element in some two-term DGLA. In that case, there were only bivectors and trivectors. Okay, and right, so that's the notion of shifted Poisson structure, and there's also notion of Poisson structure being non-degenerate. So a Poisson structure gives you a map from the cotangent complex to the tangent complex up to some shift. And again, you can just ask this to be a quasi-isomorphism. And a somewhat difficult theorem is that such non-degenerate shifted Poisson structures are the same as n-shifted symplectic structures. So exactly how you would expect non-degenerate Poisson structures as symplectic structures. Of course, the difficulty is that everything holds up to quasi-isomorphism. You have to specify all this homotypic closure data for the symplectic structure. Yeah, that's why it's all more difficult. And there's also there are also relative notions. So just like for shifted symplectic structures, there's a notion of Lagrangian structure. For shifted Poisson structures, there is a notion of coisotropic structures. So yeah, so there's a notion of a map L to X, where X is n-shifted Poisson, having a coisotropic structure. And let me mention that there, again, the new phenomenon is that the source of a coisotropic map carries a shifted Poisson structure of shift one less. Okay, so that's something new. And as an example, if you have a Lagrangian structure, maybe let's say X is n-shifted symplectic. then L carries an n-1 shifted Poisson structure. Okay, so I think Pavel pointed out this fact in this diagram that, so I'm just talking about symplectic structures. So there's a symplectic double groupoid. And I said that you just have this one-shifted Lagrangian structures, sorry, two-shifted Lagrangian structures from X to Z and from Y to Z. And the claim is that there's this forgetful map from Lagrangian structures to one-shifted Poisson structures on the source. And so Pavel reinterpreted this in terms of some Poisson groupoids. Okay. All right. So next, next I want to give some examples. In particular, I want to relate this to what Camille talked about. So let's begin with, as usual, just smooth groupoid, G over M. And let's try to compute polar vectors. And I want to talk about one-shifted Poisson structures. So I want to compute one-shifted polar vectors. Well, by definition, one-shifted polar vectors are functions on the one-shifted cotangent bundle. And I gave a representation for the one-shifted cotangent bundle of the groupoid in terms of the cotangent groupoid of G. And so then functions will be given by this homotopy limit, or if you like, the check complex, which only has in degree 0 functions on the dual of the Lie algebroid. In degree 1, it will have functions in a cotangent bundle, so polar vector fields on the groupoid. And then there are some higher terms. Okay, so this is some complex. You can truncate this complex. Only remember this in degrees 0 and 1. So you forget about all the higher stuff. So this is all that's going to be relevant. And in this case, so you get exactly the two-term complex that Camille wrote down. So in degree 0, it's going to be sections of the exterior algebra and the Lie algebroid. And in degree 1, if you truncate this, you don't get all polar vectors, but you get multiplicity polar vectors on G. Okay, so you have this two-term complex, and then Iglesias, Ponte, Larange, and Gu, and Shu introduced a DG Lie bracket of degree -1. And as I explained in the talk yesterday, this DG Lie algebra is actually Moriti invariant, independent of the choice of representation of the stack. Okay, and then you get the following results. That a one-shifted Poisson structure on the stack quotient is the same as the data of a quasi-Poisson groupoid. Maybe let me say that the implication is that quasi-Poisson groupoids are Moriti invariant because they don't depend on the choice of the atlas. And then if you want to recover ordinary Poisson groupoids, you also have to specify coisotropic structure on the quotient map from the manifold to the quotient stack. Okay. Are there any questions? All right. So next, I want to talk about some things you can do, and for So let's consider the infinitesimal case where you take quotients not by groupoids but by Lie algebroids. And I just want to explain how various sort of classical things can be seen in from the point of view of shifted Poisson structures or shifted symplectic structures. Okay, so the infinitesimal version of a quasi-Poisson groupoid So if you have a quasi-Poisson groupoid, is the notion of a quasi-Lie bialgebroid. So the Lie algebroid of G will be a quasi-Lie bialgebroid. And so in the same way, you can show that if you have a Lie algebroid, the one-shifted Poisson structure on the quotient by the Lie algebroid is the data of a quasi-Lie bialgebroid on L. So how does this relate to what I talked about before? So let's say you have a Dirac structure. So E is a Courant algebroid, and L is a Lagrangian subbundle closed under the bracket. Okay, and I said that Dirac structures give rise to two shifted Lagrangian maps. So from M mod L to M mod the corresponding Lie 2 algebroid associated to Courant algebroid. So again, if E is Courant algebroid, there's some two-term complex which looks like this. Cotangent bundle going to E via the dual anchor map, and this is a Lie 2 algebroid. Okay, and so you have this two-shifted Lagrangian map, and I mentioned that if you have a two-shifted Lagrangian map on the source, so on M mod L, you have an induced one-shifted Poisson structure. And this theorem says that a one-shifted Poisson structure is the data of a quasi-Lie bialgebroid. So what I'm saying here is that this map, forgetful map from Dirac structures to quasi-Lie bialgebroids, can be interpreted in terms of this forgetful map from two shifted Lagrangian maps to just one shifted Poisson structures on the source.
So Paolo, I guess you like identify like the global picture and the infinitesimal picture automatically, right? Like when you say shifted, symplectic, and Poisson, they can be on the groupoid. The global part can be the semi-groupoid, semi-algebraic, can also be totally algebraic part. Like they're all like but you sort of just they're like integration integration differentiation between them. But you like take them like.
Well, I would say that there's so there's the kind of the land of stacks,
right.
And inside of these stacks you have algebraic stacks, so quotients by groupoids,
right? And
then there's some kind of formal stacks in here,
right? You just quotient by DG manifold. Like you mean that?
Well, I would say did you Lie algebroid? And so these two are different classes of stacks, but you can talk about shifted symplectic structures and shifted Poisson structures on either class. Yeah. So there's a natural integration procedure, but I'm just not talking about the integration.
Sure. And for people in that group, probably it's big change because you have these forms and you also have the IM form corresponding to them. It's an effort to do that.
Right. Yeah, thanks. Okay. Yeah. Any other questions, comments? All right. So yeah, the last thing I want to mention is maybe let me also mention here. Yeah, let me just say it here. So if you have a symplectic, let's go back to the case of a symplectic groupoid. So if you have a symplectic groupoid, you have this Lagrangian map from M to the quotient, and the quotient is one shifted symplectic. So by the same forgetful map, on the source, you'll have a zero shifted Poisson structure, so an ordinary Poisson structure. So given a symplectic groupoid, on the source, you see a Poisson structure. So that's the usual procedure. And this thing that Paolo was saying about double groupoids, if you have a symplectic double groupoid, then these are Poisson groupoids. this is also the same kind of forgetful map from Lagrangian structures to Poisson structures on the source. All right, so I want to just end with some example how two shifted Poisson structures are supposed to work. So an example of a two-shifted Poisson structure you can see in nature is if you have a Dirac groupoid. So if G carries a multiplicative Dirac structure, so I guess this notion is due to Ortiz. So if G carries a multiplicative Dirac structure, then, well, so if G carries a Dirac structure, as I said, on a quotient, you have a one-shifted Poisson structure. And now you have a multiplicative one-shifted Poisson structure. So if you take a quotient by that, you'll get a two-shifted Poisson structure. Okay, so that's how two-shifted Poisson structures arise. But also, I think it would be interesting to figure out two-shifted Poisson structures on a quotient by a double groupoid. And just like the way we figure out one-shifted Poisson structures on a quotient by an ordinary groupoid, so you just need to take functions on the cotangent groupoid of Lie one groupoid. Here, to figure out what are two-shifted Poisson structures, you need to compute functions on the two-shifted cotangent bundle of the quotient stack. And so the cotangent bundle of the quotient stack is presented in terms of the cotangent double groupoid. And so in this case, you can extract a Lie 3 algebra, sorry. So it's going to be a three-term DG Lie algebra presenting two shifted polar vector fields. So it would be interesting to write down a Poisson Lie bracket there, and I guess there's some kind of notion of a quasi Poisson double groupoid. That's what you should see. Okay, so I'll stop here. Thanks.
Great. If there are any questions from the online audience, please write them in the chat and I might call on you. Otherwise,
yes. Yeah. Mackenzie introduced this Poisson double groupoids, which are basically a double groupoid with a Poisson structure of D that is multiplicative for both horizontal and vertical structure. And I was wondering what is if this structure relates somehow with this one that you are describing to us.
Yes, so this is the strict version of what I'm talking about. So this just involves a bivector on D. So basically this kind of two-shifted Poisson structure on this quotient by the double groupoid will be a bivector on D, some trivectors on, well, the two Lie algebroids. So there's going to be two lambdas. And then there's going to be a quadruple vector for the core Lie algebroid. And so this notion of Poisson double groupoid just involves a bivector on the space of double arrows. It doesn't involve anything weaker. And so that notion is not Meridian invariant, but this quasi-Poisson version is Meridian invariant. So M mod D, if you like, it's the quotient of M by the Lie 2 groupoid corresponding to the double groupoid. So it's the deepest quotient you can obtain from M.
So there's a two stack?
Yes, yes. So M mod D is a two stack. So there's some picture. Yeah, yes. So M mod D is a two stack, then M mod each groupoid is a one stack, and then M is a zero stack.
Pavel, let me ask you because I didn't get it completely. I understand that the strict notion, the Poisson double groupoid, is not moneta invariant. It's something very peculiar that you may have. But if you have this, do you have a Poisson to start, let's say, or does it induce a structure at the Taki level?
Yeah. It is possible to show that basically this kind of statement, I haven't worked it out, but I'm sure someone can work it out. Just complete analog of the statement. If you replace symplectic by Poisson, and in this theorem you replace two-shifted symplectic by two-shifted Poisson, two-shifted Lagrangians by two-shifted quasi-tropics, and so on. So there's going to be the same statement. So there will be a two-shifted Poisson structure, but then there's a lot of extra structure, sort of trivializing all the trivectors and so on.
Okay, thank you.
Yeah.
Pavel, could you address Luca's question in the chat?
Yeah. So there's a question about Riemannian metrics. Indeed, maybe. So the answer is no. There aren't definitions in the world of derived algebraic geometry, just because algebraic geometers don't care about kind of algebraic metrics. You care about smooth metrics. So I think it would be very interesting to. I guess there's a work by Del Hoyo and someone else whose name I forget, defining Riemannian structures on quotient stacks. It would be interesting to interpret. Rui Loja Fernandez, and it would be very interesting to sort of get some kind of derived perspective on that.
So next question is from none other than Rui Fernandez. Please go ahead.
Can you say a few words about the formal case in the differentiable side? So say, for example, if I think of a formal stack as a germ of a locally groupoid, what would be a moneta equivalence between two such germs?
I would say this is going to be, again, a local groupoid. Right. So let's try to go back. So the Morita morphism will be an isomorphism here in the formal case. And then, you're allowed to sort of make the local Lie groupoid even smaller.
It's much stronger.
Yes, it's stronger for Lie one groupoids. If you have a higher Lie groupoid, you can imagine replace. So you can imagine replacing the DG Lie algebroid by something quasi-isomorphic. Of course, if you have an ordinary Lie algebroid, isomorphic just means isomorphic. But for higher Lie algebroids, you can say quasi-isomorphic Lie algebroids.
Is this worked out somewhere, or
I don't know. No, maybe Chen Chang would know.
I'm sorry. I just I was at like answer Rui's other question. What was the question?
So actually, we don't really have time to go on, but could you address Joao's question just to finalize? There's a question in the chat.
Yes. Let me write it where I have space. So there's a example of integrating Poisson Lie group. So the double. So there's if you have a Poisson Lie group, you have this kind of diagram, and this is going to give rise to this diagram of stacks. So point mod D. Point mod G, point mod G dual, and point. So the two-shifted Poisson structure on, so this one will be two-shifted Poisson. There's a strict way of saying that. It's just a Casimir element on the Lie algebra of the double group. You can also interpret this in terms of some Dirac groups, but yeah. So in this case, two-shifted Poisson structure is just this Casimir element. So there's an element in Sim2 of the Lie algebra, and that is the two-shifted Poisson structure for the integration of a Poisson group. Okay.
Okay, thanks, Pavel. We're going to resume at 10 o'clock, but we'll leave the chat open so that participants can continue with their questions. Let's give Pavel another thank you.